Hello, this is Jack Jackson back with more History of Mathematics videos. Um, in this video, we're going to talk about geometry in the 19th century. Now, in the last video, we talked a lot about the discovery, creation, development, whatever, of non-Euclidean geometry, specifically what we now call hyperbolic geometry. And the main players there were Bolyai, Lobachevsky, and Gauss. Earlier work was done by folks like Lambert and Sacchieri and others. So this was the culmination of actually centuries of work looking at Euclid's fifth postulate, trying to prove it, thinking it was dependent on the other postulates. It turns out it's independent, and this was really, uh, you know, earth-shattering, groundbreaking stuff because this really changed the way we look at mathematics a lot. It changed the way we think about geometry. And of course, geometry study was really the foundation of mathematics back with the ancient Greeks. And when the Greeks were looking at it, they were saying, okay, this is these postulates and axioms of Euclid. They were just a statement of the way things had to be, a statement of the obvious characteristics of the real world, or at least an idealized version of it. At least that's the way they were thinking of it. And after they discovered hyperbolic geometry, and then some later work on spherical geometry as well, they realized, hey, maybe there's a different way to look at geometry. We can look at geometry as having a set of axioms, and we can work with those axioms and see what we can do. And then there's an idea of applying that to all of mathematics. So that's I can't overstate really how important uh, a result that was in the history of mathematics. That was around the early 1800s, around 1825 or so, uh, plus or minus a little bit, when you started getting that published. In the mid 1800s, we had work on geometry of surfaces by Gauss, and especially Riemann. And so now we're thinking of, like Euclidean geometry being geometry in a Euclidean plane, spherical geometry being geometry on a surface of a sphere, where that's the plane, and hyperbolic geometry being the surface of um, they call it a pseudosphere, is one way of looking at that. In 1854, Bernard Riemann defended his dissertation on the hypothesis which lie at the foundation of geometry, and that's kind of a groundbreaking work. And among other things, it led to a study of what's now known as differential geometry. In 1868, Hermann von Helmholtz looked at geometry or geometric manifold of arbitrary dimensions, expanding the study of geometry into multi dimensions. Uh, Not so much an important mathematical work, but kind of a fun little book was written called Flatland by Edwin Abbott Abbott in 1884. It was a satirical novella, and it was satirizing Victorian social structure, but it also introduced the concept of higher dimensions to non-mathematicians. And it's endured really because of this interesting way that it is introduced higher dimensional mathematics, higher dimensional geometry. A little bit before that, back in 1844, Gaussman studied n-dimensional vector spaces and started visualizing them geometrically. So you're starting to see there's a lot of different ways of looking at geometry, connecting them to things like vector spaces, connecting them to calculus. Then models for hyperbolic geometry developed in the late 1800s. Beltrami and Poincaré. Again, I mentioned on the geometry on a pseudosphere, but then there were also at least two different plane models. One was where you think of the hyperbolic plane as being the points on the interior of a circular disk. Lines then are either diametrical chords, a diameter going through a line segment going through the center of the chord, center of the circle with endpoints on the circle. These points on the circle itself were considered at infinity, not part of the model. And then other lines were um, circular arcs with endpoints on the circle, and where they were perpendicular to the circle. Uh, if you take that model and do a circle inversion with it, you get a half plane model where all the points are in a half plane, say with positive y coordinates, for example. The x-axis then becomes the edge of that plane, which is where the, the circle itself gets mapped to in that circle inversion, and that becomes the points at infinity. Lines then are two types. The ones that are vertical rays perpendicular to the surface, to the edge, and then the other one is semicircles with center on the edge and endpoints on the edge. And when I work with hyperbolic geometry in my geometry class, I typically use that Beltrami Poincaré half plane model. But hyperbolic geometry was not the only thing that we were working on. There were projective geometry as well. Projective geometry, you may remember, was introduced all the way back in the back in the Renaissance anyway, to start looking at ways of doing perspective in geometry, perspectives in drawings and art, and so forth. That led to studies in projective geometry, but that was advanced quite a bit in the 19th century by by people such as Jean-Victor Poncelet. Uh, he had a work in 1822 that was important there. Michel Chalet, Julius Plücker, and Arthur Cayley. We've talked about Cayley before in the context of looking at matrices and also in abstract algebra. Another thing that Poncelet developed was the idea of dual geometries, where points in one geometry are mapped to lines in another geometry and vice versa, with incidence reversed. So, for example, if L and M are lines that intersect at a point A in the first geometry, then f of A is a line in the second geometry that contains points f of L and f of M. Chalet introduced a cross ratio. It's a ratio of distances that remain invariant under projection. That was related to projective geometry. And Cayley in 1859 introduced the definition of a metric in the projected plane. So now look at how far we've come from thinking of Euclidean geometry as like the only geometry. Now we have these projective geometries. We can even talk about comparing two different geometries now, and we've got all these different ways of looking um, at different geometries. Okay. In the late 19th century and into the early 20th century, Felix Klein connected projected geometry with non-Euclidean geometries via the use of a metric. And he also placed spherical, hyperbolic, and Euclidean geometries on equal footing. Now, basically, you can look at the three possibilities there for the parallel postulate. Euclidean geometry says if you're in a plane and you've got a line and a point not a line, there's exactly one line through that point that's parallel to the given line. In spherical geometry, if you're given a line and a point not a line, there are no lines through that point that are parallel to the other line. All lines must intersect in two points where on opposite sides of the polar opposite sides of the sphere, like the North Pole and South Pole, for example. In hyperbolic geometry, if you have a line and a point not on the line, there are infinitely many lines through that point which are parallel to the given line. This also relates to the angles in the triangle. In Euclidean geometry, the angles in a triangle add up to pi radians or 180 degrees. The measures add up. Whereas in spherical geometry, the sum of the anterior angle measures of the three angles in a triangle always add up to more than pi radians or more than 180 degrees. In hyperbolic geometry, the sum of the interior angle measures is always less than pi radians, less than 180 degrees. And so you can think of these as doing geometries on three different surfaces. You can think of these and it's related to the idea of curvature of those surfaces. This also led to to the study of metric spaces, and then ultimately a an extension of that to topology. Topology is a major area of research in the 20th century and beyond. Klein also introduced a transformations approach to studying geometry. He had his Erlanger program studying geometries from the viewpoint of properties that are invariant under certain types of transformations. And that was pretty transformational in the way we looked at geometry and the way we looked at mathematics as well. Graph theory kind of grew out of geometry. We also mentioned earlier how it goes, we can trace it back to Euler's treatment of the Königsberg Bridge problem, but it started to take off a little bit in the 19th century. It was applied in a few different areas, and that becomes a bigger area of research in the 20th century and beyond. And so graph theory was applied to solving certain geometric problems. One of them that was pretty interesting was the four color problem. The idea is if you have a map, like say a map of the states of the United States or countries of the world or whatever, if you're talking about it on a plane, and you draw that map and then you color in each of the regions with different colors. How many colors does it take to color the map so that no two adjacent pieces have the same color? Okay, so if they meet at a point, it doesn't matter. But if they meet at anything more than a point, any kind of a little line segment or curve, then those on both sides can't have the same color. Well, depending on the map, it might be able to do it with two colors or three colors or four colors. But the conjecture is that it only takes four colors. That you couldn't find one that you couldn't color with uh, with just four colors that way. And some work was working on this in the 19th century. Some work was applied there, and it used graph theory to help with that. It actually wasn't solved until the 20th century. In the late 19th and 20th, and by the way, it's true, it's just four colors is all that's needed. In the 19th century and the early 20th century, Moritz Pasch became the father of rigor in geometry as he worked on the foundations of geometry. He pointed out several assumptions made by Euclid that were not explicit in his postulates and axioms. So Pasch really went um, back to Euclid and said, okay, now that we've seen all these different things that can happen with hyperbolic geometry and spherical geometry and so forth, what do we really need to have to get Euclidean geometry? And he realized that there were actually several assumptions made by Euclid that were not explicit in his postulates and axioms, and he did some work on that. That was picked up later in the 19th century and the early 20th century by David Hilbert. David Hilbert becomes pretty much a giant in mathematics at the end of the 19th and early 20th century. And he came out with a more rigorous set of postulates for a synthetic approach to Euclidean geometry. He came out with those in 1899, so right at the very end of the 19th century. And he became with a reworking of Euclidean geometry where every single thing was made extremely explicit. And his geometry program that he worked out there uh, really finally really cleaned up the stuff in the elements and gives Euclidean geometry a very completely solid footing and cleans up any little problems it might have had. And this Hilbert's approach then became the basis really for all further study of geometry. Um, and he also applied equal amount of rigor to some non-Euclidean geometries as well. So those are some of the advancements in geometry in the 19th century. Let's just take a quick look at some photographs or photographs and drawings of some of the major players here, kind of in no particular order. Uh, here's Moritz Pasch, very, very important for establishing the foundations of geometry. He was German. He lived from 1843 to 1930. So if you notice, some of his work would have been done in the early 20th century as well. Hermann von Helmholtz was German from 1821 to 1894. He worked in multidimensional manifolds. Edwin A. Abbott, 1838 to 1926 in England. He was the author of Flatland. He was a school teacher. Marcel Grossmann, from 1878 to 1936 in Switzerland, worked with n-dimensional vector spaces. Jean-Victor Poncelet, from 1799 to 1867, was French. He's the one that came up with the idea of dual geometries. Eugenio Beltrami, from 1835 to 1900 in Italy, worked in differential geometry. He's also one of the ones that helped come up with some of the models that we have for hyperbolic geometry. Julius Plücker, from 1801 to 1868 is German, worked in analytic geometry. Arthur Cayley here was important for some algebra matrices, but he also did a lot of work with geometry and n-dimensional geometry. He's from England, lived from 1821 to 1895. And Michel Chalet was French, lived from 1793 to 1880, and he did work on projected geometry. And of course, Bernard Riemann was extremely important from 1826 to 1866. He was German. He worked in non-Euclidean geometry. I didn't list Gauss, Belai, and Lobachevsky here because I showed you their pictures and talked about them in the previous video. And then finally, two giants in geometry from the late 19th century and on into the early 20th century were Felix Klein and David Hilbert, both from Germany. Klein is the older gentleman. He was born in 1849 and died in 1925. David Hilbert, from a generation or so later, born in 1862 and died in 1943. Klein worked in transformational geometry. David Hilbert worked on the foundations of geometry. Both of these made really great advancements in geometry at the end of the 19th century and on into the 20th century. I gave a little bit of a bio of Felix Klein in the last video, and when we get to the 20th century videos, I'm going to talk a little bit more about David Hilbert and some of the other things that he did, because he was a remarkable mathematician who did a whole bunch of different things. One of the last real generalists in mathematics, where he did a wide variety of different fields. So geometry was an interesting field of mathematics. When you think back, it's where we started when we looked at the work with the ancient Greeks. That's the first work that really lifted mathematics up to a real serious, rigorous field of study. And the work with the pioneers there of place of people like Euclid and of course Thales before that, and Euclid and Archimedes, Pythagoras, not necessarily in chronological order there, but some important folks back, and several other Greek mathematicians. And and really, not since the time of some of those ancient Greeks had you ever had this much advance in geometry than you did in this time period in the 19th century. Really, kind of, yeah, not all of the 19th century really, and up into the early 20th century.